So welcome to our third lecture, dealing with Voltaic cells. What would be the potential of the following cell given the indicated concentrations? Well, the first step, of course, is we have to decide what's actually going to be happening, what the actual reaction is, in which way the electrons are actually going. So we have to look up on our redox table the potentials for the possible reactants. The tin-4 reduction to tin-2 has a potential of 0.15 volts. The chromium plus 3 to chromium 0 has a potential of minus 0.74 volts. So since the tin has the more positive potential, it's the one that's going to be running as written. So one of our reactants is the tin-4, and one of the products is the tin-2. The chromium reaction has to be running backwards since it has the less potential. That means the chromium metal is one of the reactants and the chromium plus 3 is one of the products. So the potential of the cell is the potential of the redox reaction and the potential of the oxidation reaction. The redox reaction is the tin, so it's plus 1.5 volts. And the redox potential, the oxidation potential is the 0.74 volts, but it's running backwards, so it's got a positive 0.74 volts, and so the total potential of the cell is 0.89 volts. But that would be if everything was 1 molar under standard conditions. We don't have those concentrations, so we have to use the Nernst equation. The potential of the cell is equal to the epsilon 0 minus 0.0591 volts divided by n, the number of electrons transferred, times the log of Q. And so the next step is we're going to have to balance the equation. The tin is gaining 2 electrons, whereas the chromium is losing 3 electrons. So 2 and 3, we're going to have a 6 electron transfer. That means we're going to need 3 of the tin-4s for every 2 of the chromium atoms, and we're going to get 3 tin-2s and 2 chromium plus 3s as the products. So the E0 is 0.89 volts minus 0.00591 volts divided by 6 times the log. The chromium plus 3 and the tin plus 2 are the products. The chromium metal and the tin-4 are the reactants. Put in those concentrations and we find so the potential of the cell, the 0.89 volts, which is the E0 minus 0.0591 volts divided by 6, the log, chromium plus 3 concentration squared, tin-2 concentration cubed divided by the chromium metals concentration squared and the tin-4's concentration cubed. Put in those concentrations, we get 5,000, so the log of 5,000. So 0.0519 divided by 6 times 3.699, and we find out that the potential of the cell, as written, would be 0.85 volts. So what would be the delta G for this cell? Well, delta G is equal to minus NFE epsilon. So that's a 6 electron transfer. A Faraday is 96,485 coulombs. The potential for the cell, 0.85 volts. And therefore, we get a delta G of 492 kilojoules, minus 492 kilojoules, since it's a spontaneous cell. So what would be the equilibrium constant for this reaction? Well, at equilibrium, the potential of the cell is 0. So it's the epsilon 0 minus 0.0591 volts divided by n times the log of K. So the log of K is 0.69 times 6 divided by 0.0591. So 90.3510. And so 10 to the 90.355 the equilibrium constant would be 2.3 times 10 to the 90th. Suppose we had two beakers, side by side, separated by a barrier. In one we had a solution of 1 molar copper plus 2 ions, and in the other one we had a solution of 0.01 molar copper plus 2 ions. What would happen when we made an opening in the barrier? Well, what would happen, of course, is the two solutions would mix together, and eventually we'd end up with a solution with one uniform solution. And what's the driving force for that? Since there obviously isn't going to be any energy change, there's no work being done, and it's not getting warmer or colder. And the answer, of course, is it's an entropy effect. By spreading out, the higher concentration manages to increase its amount of entropy, while at the same time the lower one's also spreading out, so it's simply an entropy effect. So what would happen if instead of a glass barrier between the two, we had a barrier that was made out of a sheet of copper? What would be happening now? Well, we'd have copper ions in contact with copper metal. And when copper ions run into copper metal, you can get an exchange of electrons. This doesn't produce any apparent effect, of course, because you change a copper atom to a copper ion while changing a copper ion to a copper atom, and so there doesn't seem to be any net change. So would there be any net change in this case? In this case, yes. And why? It would be, in this case, because there would be 100 times as many copper ions hitting one side of the copper sheet as hitting the other. And so there would be more collisions on one side than the other. But the copper sheet doesn't care about where the collisions come from. It's simply going to uniformly release copper ions all over its surface, which means it's going to put as many copper ions into the left beaker as it puts into the right beaker. But 100 times as many copper ions are going to be reduced on the left as it's being reduced on the right, which means as time passes, the number of copper ions getting reduced on the left will be much greater than the number of copper ions being reduced on the right, whereas the number of copper ions being released from the metal will be the same on both sides. And the effect is, well, it'll keep going until both concentrations are equal again, because that, of course, is what entropy wants to have happen. Let's change things again. Let's go with two separate beakers. And this time, rather than having a piece of metal separating our two solutions, we'll simply have a piece of metal that spans both of the different beakers. In this case, we're of course going to have to add the salt bridge so that the charges stay balanced. And now what are we going to see happen? So what's going to happen now? Well, chemically, as far as what's going to happen, the copper ions and copper atoms think the two situations are identical. You got a copper ion solution in contact with a piece of copper. And so there's going to be oxidation and reduction. And in the same way, there are a lot more copper ions hitting the electrode on the left than hitting the electrode on the right. And so again, we'd have exactly the same thing. Well, this time it's a little bit different. And what's different about it, of course, is the piece of wire. The electrons have to leave the right side electrode and move over to the left side electrode to reduce the copper ions that are hitting over there. And therefore, we are in fact getting a current passing through the wire. So we have what is known as a concentration cell. And what would the potential for the concentration cell be? Well, its epsilon is equal to epsilon 0 minus 0.591 volts divided by n log Q. Well, of course, the potential is 0 since the copper ions are being both oxidized and reduced. The number of electrons being transferred is 2. And of course, it's the log of the copper ion concentration times the copper metals concentration divided by the copper metals concentration times the copper ions concentration. Well, the concentration of the copper metal, of course, is just 1. But which one of which goes into the copper 2 concentrations? Well, at this point, logic shows up. Where are the electrons going? Whose concentration is going up? Well, it's the lower concentration that would be going up. So automatically the lower concentration is the product side. The larger concentration is the reactant side. And so 0.01 divided by 1 times 1 divided by 1 is simply 100. 0.01, the log of 0.01 is minus 2, so minus 2 times 0.0591 volts divided by 2 means the potential of that cell would be 0.059 volts. Notice that if you get those concentrations wrong, when you take the log, you'll get a positive number, which means the potential for the cell would be negative, which means, of course, yes, it's running in the other direction. You got the products and reactants wrong. Which brings us to the end of today's lecture on voltaic cells. We have one more lecture on voltaic cells, and then you should expect an exam. So yes, somewhere around Friday this week, you should be receiving an exam. And just like the first one, there's a form for your parents to fill out. You have 1 hour to work on it. As soon as you get it done, you need to mail it back to me. Okay, so have a good day.